Hello, this is Costa, and today I'm doing a presentation on my paper, Frame Skipping with Deep QLearning as a General Technique. So before I delve into the details of the paper, I have to give you a little context on what is reinforcement learning. Reinforcement learning is one of the most popular techniques these days to teach agents to play computer games, at least in academia. In the industry, it's a little different. But essentially, reinforcement learning is a mechanism through which an agent could perform certain actions to the environment, much like a human would do, and then you would receive some sort of feedback in the form of scalar rewards, and then also you will receive a new observation of the environment so that you can observe what you did and how it affected the environment. And hopefully you take the feedback, the scalar reward, to somehow modify your behavior such in a way that you could maximize your future rewards. So what I did for the project is to introduce frame skipping technique to some non-arcade games. So previously, it is known that frame skipping is very useful to train agents playing Atari 2600 games. But in general, the games that apply the frame skipping techniques are the games that you use a controller to play like 30 years ago. What I was interested is to see whether this technique could be applied to just any sort of problem. Or in my case, I want to see whether it could be applied to some more recent problems. And then basically I sampled four environments from OpenAI Gym, which provides a standard interface of reinforcement learning. So that I pick those four environments. Taxi V2, it's an environment where you're essentially driving a taxi to pick up passengers and dropping them off to get rewards. And Frozen Lake, where you have those tiles that are safe, or some tiles are not safe, and then you're trying to save yourself. And also, this is the cart pole, one of the most classic environments. As an agent, you're trying to balance the pole such that it doesn't fall below a certain angle. And also, this is Acrobat V1. Essentially, you're trying to swing the end of the robot link to a certain height. All these problems are difficult in their own ways. Like when you see the environment, you thought they're very easy because it's very intuitive for humans to come up with solutions for these kind of games, but it's actually really difficult. Partially because of the exploration versus exploitation problem. For example, for Taxi V2 problems, implementation has been very, very difficult in the beginning because the agent what they tend to do in the beginning is to basically say, go right, go right, go right, and just never try anything else because the reward is so delayed. You have to pick up the passenger from this position and drop it off at that position to actually receive a reward. And then if you just execute actions, pick up or drop off in any other location, you will get a negative reward. So the agent is not incentivized to do pickups or drop-offs. So it's really hard for the agents to learn which agent to pick up. At which position should pick up, and sometimes you just get stuck in this local maximum where you just keep going right or keep going east all the time without trying anything else. Well, I have to talk about what is frame skipping. Frame skipping is basically a technique that, as its name suggests, that you skip a couple frames. So you repeat the same actions you just executed until the keyframes have been skipped. The benefits definitely include that you could save a lot of computational power because when you're skipping frames, you're just executing actions. You're not really doing anything, so you're not doing trainings, you're not evaluating your policies, you're just executing the actions you've done before. It could save a lot of computational power. But also it could lose important information for training purposes. And the intuition behind the frame skipping is actually pretty intuitive. It's like human in a way. When we play games or do anything in general, we don't pay attention 100% of the time. Sometimes we perform the same actions over and over again, while the other times we need to focus more and then switch it up a little bit. And in a way that is similar to frame skipping, because sometimes you really don't need the agents to keep doing the same actions over and over again, evaluating the same thing over and over again. You want to save some computational power, but there are some drawbacks associated with frame skipping. So this is my modified version of the deep QLearning. Specifically, this part of the code, this if block and this if block are what is being added to make sure that the agents will skip keyframes before doing the policy evaluation and doing the updates again. And it's a pretty standard DQN deep QLearning algorithm where you have a replay memory. Essentially, every time you perform an action, receiving rewards, all that kind of things, you record the transition so that you can sample it later. This is to make sure that you're relearning the things that you do. So it's almost like I have a bank of transitions. From state t to state t plus 1. If I execute action t at state t, I will receive reward t. So it just kind of helps you to relearn some of the things that you have already learned so that you don't forget. And then basically you're using this future information. It's kind of hard to get into the details. You kind of need to read the source code yourself. But essentially, you're using a temporal difference to update your policy. You're using after you have already executed the actions, you're using future information to update a Q-table approximation. Well, I won't dive into detail of those, but essentially it bootstraps you learning, and then essentially you kind of converges. So this is the experiment results, and then as you can see, very interestingly, if you're just skipping one frame per time step, so for what that means is frame skip equals 1, meaning that you're only training the agent at time step 0 to 4, 6. So you're skipping one per turn, and this is the result that we get. So no skipping at all is 0, and some skipping is 1. As you can see in all of the environments, their performances are very similar. In some cases, the frame skipping actually outperforms. So for example, in a Taxi V2 environment, as well as in the Acrobat V1 environment. It's kind of hard to see the carpool V0, what's happening over here. But also just in the Frozen Lake, you can see their performances are very comparable. However, once you start to skip more frames, then we can see the performance started to degrade. So for the frozen lake problem, it basically stopped. It doesn't really learn anymore. It just kind of gets stuck in here. Frozen Lake is actually kind of an interesting environment. You get reward 0 for all the game until you made it to the exit. So that's why you see good performances is reaching 1. It's also a very difficult problem because the reward is it's very delayed or sparse, as they call it. Yeah, and for Taxi V2, it's the same problem. So yeah, this is the experiment results, and for the future work, I was hoping to incorporate the result by Sharma, ETAL. What they basically did is to do a dynamic sort of frame skipping. So instead of doing a static K frame skipping that you have to determine at the beginning of the game, what they did is to come up with this collection of value functions. So where each value function at state S and performing action K represents the return that the agent would get on taking action AK in state T and following the optimal policy thereafter. So essentially it's saying, if this actions that if I keep taking these actions, I could get a really good value. I'll just keep doing it, and without I can just do it and skip frames for a long time before I have to reevaluate the situation. I think this is an interesting idea, but it's definitely going to take some time to evaluate. But yeah, this is about it as far as the presentation goes, and this is kind of what the code looks like. The only difference between the continuous and the discrete is how you build a neural network in the first place. For the discrete case, you have this one-hot encoding because you want to treat each integer as a category versus just a regular floating point number. But other than that, it's all the same. And the way you run it is you run the continuous command, you execute those, and they'll generate outputs. They'll generate the rewards in the respective folders, and eventually you run this main.py to generate the images. And that's about it. Hope you liked it. Yeah. Let me know if you have any questions. Thank you.